So today I'll discuss the differences between auto meshing versus manual meshing. I'll go through a couple examples showing in detail how the shell and beam meshing tools work. And finally, I'll discuss the application of the auto line constraint to show the power of this feature. Okay, so just a quick overview. So what is meshing? So mesh is a network of line elements and interconnecting nodes used to model a structural system and numerically solve its simulated behavior under applied loading. So in object-based modeling environments, engineers can generate structural models by drawing area objects that physically define the structure itself, such as wall panels, floors, and/or ramps. So in this example, I'll talk about auto meshing. So all auto meshing is internally done by ETABS. So it keeps shells as a single piece, and we'll go through a few of these examples here today. All right, so what are we looking at? Let's talk about some global meshing features that are assigned to all shells in ETABS. So to access this, we'll go underneath the Analyze menu and click on Automatic Mesh Settings for Floors. So again, I really want to reiterate, this applies to all shells in this specific model. All right, so what are the options here? General mesh, that's what we're looking at now. So this is the default option and is typically the recommended option for all slab geometries. So the mesh generated will predominantly use 4-node quadrilateral elements, as you can see here, supplemented with triangular elements where needed. So if I zoom in here a little bit, you can see, well, we'll do that after we assign this. You can see there are some triangular elements in here as well. So this is highly recommended if the slab geometry is irregular. So you can see for this model, the slab edge is a little rounded. It is not your typical rectangular slab. There are some diagonal elements, some curved edge geometry. So this general mesh is recommended for this type of irregular type of slab. So the mesh generated may appear somewhat arbitrary and non-symmetric, as you can see here. So what we're viewing here is the general mesh. Okay, so what are some other options? So this rectangular mesh is the next one. And this option is typically recommended for more rectangular type slab, more regular slabs. This option restricts the quadrilateral elements, as you see here in the general, to be used in rectangular and is acceptable for rectangular slabs. So this option will create substantially larger number of elements in the analysis model, which can significantly affect computational time. Excuse me. So let's take a look at this. So we're looking at general mesh. I'm going to click on rectangular and click OK. So we've selected the approximate maximum mesh size of 4, and we'll touch upon these here in a minute. So if we click OK, and we click on the Set Display Options button, this is where I can go and select Shell Analysis Mesh. So this is how I can select the mesh, and it can be shown to me graphically on the screen. So if I click Apply, just takes a second to regenerate. You can see in the bottom left-hand corner of the screen saying Creating Analysis Model. Okay, a little different than the general, right? It's more rectangular and is not necessarily recommended for this type of more complicated slab. So you can see here, there are some very tiny slivers of elements which will cause load distribution, but will not be as accurate as the general meshing tool. Now let's go back and take a look at a couple other options here. So what does this mean? What is use localized meshing? Essentially, when this option is not used, an initial grid is defined that has lines passing in two meshing directions through all joints in the structure. So let's deselect this and let me show you how that updates the mesh. So if we'll not select this and we'll click OK. Again, this just takes a couple seconds to regenerate. So again, I wanted to reiterate that all of the options underneath the Analyze auto meshing settings for floors is on a global level for all shells in the analysis. So you can see here, I'm just trying to emphasize the point that this is not a good meshing scheme for this type of structure. So you can see all the lines are very close together, and meshing looks very messy and splotchy. So trying to, for this specific example, really pushing the point of using the general mesh type option. And in the next examples, we'll talk about rectangular meshes having a better use and a better option for those types of models. Okay, we'll leave this one open and we'll come back to this. Okay, so this is kind of a little tabletop model. So floor meshes, as I was saying, are used internally by the program to distribute vertical loads to beams, columns, and walls to determine the in-plane and out-of-plane stiffness. All shell objects use model floors are automatically meshed by ETABS in the analysis model. So as you can see, this is pretty obvious. I'm using the general meshing tool here. So this is a very interesting example. I'm going to illustrate how meshed shells distribute loads to the beams. So in this case, if I right-click on the shell, we can take a look at what meshing has been assigned. This says default or general. And on the right-hand side, we have floor meshing, so no auto meshing has been assigned. So how do you do that? How do you assign these types of parameters to the shells? So I can simply select the element, and I'll go to Assign, Shell, Floor Auto Mesh Options. Okay, so what does default mean? There's a little insignia here that you can put the cursor on. It gives you some more information. What is the default option? So it says, as you can read here, a setting will be used on all shell floor objects unless another choice is specified. It says horizontal slabs use the automatic rectangular meshing or general meshing, as I talked about before, and that is being assigned here under default. So what are some other options? It says I can use for defining rigid diaphragms, no stiffness. So what this means essentially is no vertical load transfer will occur. Applies to only horizontal floors. Second option, no auto meshing. That is what has been assigned to the slab on the right-hand side. No meshing will occur. So once we run the analysis, we'll see how that will affect load distribution to the beams. And we'll show you that here in a minute. Meshing objects into, say, 3x3 or 4x4 elements is another option that the user can use. This, again, is for more typical type, rectangular type slabs, such as this one. So elements can be applied to 3 or 4 noded objects with no curved edges. Curved edges like the model I'd shown you previously. And there's many more options here. Meshing at beams, other meshing lines. And again, this type of meshing is only applied to horizontal floors, not ramps. For more complicated type structures that have many visible grid lines, say perhaps grid lines that show locations of shear walls, they can be meshed at those specific locations. Or you can just say, okay, I want to mesh every 12 inches and have it very densely meshed in that fashion. And let's go and run the analysis, and I'll answer a couple questions here as we move along. Oh. Okay, well, I did that. So I clicked OK, and it was very densely meshed. So this is it's showing you the mesh. Let's make this a little easier to view. Oh, I think you can see that. It's very densely meshed every 12 inches or so. So if we run the analysis here, let's take a look at how load distribution is going to occur. So that's a very common question as well. Okay, what if I have a very densely meshed slab as this versus a very coarse mesh slab? Is that going to affect load distribution? The answer is very slightly. I mean, the loads are going to be applied to the beams and columns directly if the slab is meshed correctly. It's not going to have a major difference if you have a very densely meshed slab versus coarse. Let's take a look at some output. If I click on display frame, and what I assigned was a uniform load to the shells and a live load, so no dead load is included in this. And if I click apply, you'll see that the loads from the slab, the uniform loads that was applied to the slab, has been distributed nicely to the beams themselves and the columns. But look, on the slab that had no mesh assigned to it, the loads were only applied to the columns in the four corners. So if we take a look at this in 3D, you can see the moments have been applied to the columns as well as the beams. And if I take a look at axial force here, you'll see on the right-hand side of the model, just loads to the columns were applied. So meshing is important, and you need to mesh the slabs for proper load distributions to the beams and columns. Okay, let's take a look at one other item here. Okay, let's go ahead and unlock this model, and we'll use this one on the right-hand side. Let's turn on the mesh again. So what I'm going to do is I'm going to apply a beam to this model. Is that mesh on? Sorry. Okay, you know, I'm going to go and assign a general mesh again to this. There we go. Okay, so this is, again, a very simple model. What if I wanted to add a beam to this? Add a frame diagonally. How would that affect the mesh? So if I click from point to point here, and the general mesh has been turned on. So you can see it recognizes that the beam has been added. And I'll turn on the extruded view to make this a little more easier to view. So it recognizes the beam going diagonally and has created mesh points along the edge of the beam. Okay, so what if I didn't want this beam to be included for whatever reason? It was below the slab, not a part of the slab itself, and I didn't want to have this included in the mesh. How could I do that? So what we can do here is select the frame element. We'll go to Assign, Frame, Frame Floor Meshing Options. And there's three options here. Program Determined, which will, of course, include the beam in the mesh itself. Include selected objects, but I'm going to include Do Not Include Selected Frame Objects in Mesh. So simply click on that. We'll click Apply. And you can see now that the mesh has been updated. Let's to not include the beam in the mesh itself. I'm going to select this and go back to Assign Shell, and we'll click on Default to get all the default properties back. There, a little more easier to view now. If I zoom in here, you can see the mesh points do not coincide with the beam at all. So a couple other things. I've shown you ways to change meshes to the slab element. Now what about the frame? So if I click on the frame, you'll notice if I go to Assign, Frame, Frame Auto Mesh Properties, a similar dialog box pops up. Again, there's options for no meshing, auto mesh frame objects, and these are the parameters. It's going to mesh at intersections with other frames if need be. You can define a minimum number of segments or a maximum segment length. So again, this is all auto meshing. It's not going to actually physically break the beam into pieces. There's another tool to do that, and we'll get into that here in the next model. So everything I've talked about so far has been all about auto meshing, not manual meshing. We'll talk about that here in the next model. Okay, so one last note, I want to talk about the mesh at intersections with other frames and edges. So this essentially divides or meshes the selected element at any intermediate joint along the element, as well as any joint where a frame or edge intersects with the element. So by default, ETABS automatically meshes elements in this manner. So this is the default when you click on auto mesh frame objects. Okay, we'll leave that model up. We'll move to the next one. Let's talk about some manual meshing. All right, so everything I've discussed so far has been auto meshing. Let's talk about manual meshing now. Auto meshing and manual meshing will produce similar results. That's a very common question. Manual meshing is much more time consuming. Typically, and this, are the sophisticated auto meshing procedures of some CSI software, it may produce a more efficient and reliable mesh. All right, so let me show you how to use the manual meshing capabilities. So I'm going to combine a couple things here. We'll talk about manual meshing and also the auto line constraint in this model. So I'm just going to delete a couple of these and start from scratch here. Leave that third wall there. Okay, so what I'm going to do is I'm just going to click on the Quick Draw Wall tool, generate a couple walls here. So now we have essentially 3 walls. I'm going to mesh these manually in a few different fashions. So what we'll do here is I'll select this first wall. So remember, if I was going to auto mesh, which is internal meshing, I would have gone to Assign, Shell, Floor Auto Mesh Options, and have ETABS break the wall, or excuse me, Wall Auto Mesh Options. Break the wall into how many pieces? I'm going to do 5 by 5. I could do 5 by 5 here, and that would internally mesh the wall, but keeping it as a single piece. So for this example, I don't want to do that. I want to physically break the wall into 5 by 5 pieces. So to do that, I'll go to Edit, Edit Shells, Divide Shells. You'll notice it's a very similar dialog box, but in this case, I'm going to click 5 by 5. Similar options available. I could have used Cookie Cut if there were some beams. I would mesh at the selected frame objects. I could divide these into quadrilaterals based upon existing visible grids, selected objects on the joints, or frame objects as well. I'm just going to do 5 by 5 for this example. Okay, and before I click OK, it gives me a little bit of a preview. Okay, before I click OK, this is what it's going to look like. And I'll do the same for this one. But I'm going to make a little bit of a change here on top. I'm going to make this 4 by 4. So here we have a situation with some mismatched nodes. So that's a very common question as well when it comes to meshing. What happens to load distribution if the nodes aren't exactly matched? So we'll get into that in this example. Okay, so Here we'll do the same thing, 4 by 4 on top, 5 by 5 on the bottom. Okay, so what do we have here? We have a situation, if I click on each one of these walls is an individual, has been broken up into 5 by 5 pieces, which means they have been manually meshed, physically meshed, broken into physical pieces. So what's a common issue with this? I'm going to zoom into this little portion of the wall here. For mismatched nodes, load distribution can be a problem typically in finite element analysis. ETABS has fixed this issue by introducing the auto line constraint. So if the meshes on common edges of adjacent area objects do not match up, such as here, automated line constraints are generated along those edges. So these constraints enforce a displacement compatibility between the mismatched meshes of adjacent objects and eliminate the need for mesh transition elements. In years past, in some programs, you'd probably have to put a little dummy element for connectivity here. So we have something called the auto line constraint that takes care of this. So let me show you how this works. So just quickly, I'm just going to assign a lateral load on top here so we get some displacement in a lateral direction. Just going to make it a couple kips. Okay, so how do I assign this auto line constraint? So if I select on these area objects here where the mismatched nodes are located, I can go to assign shell auto edge constraint. So let's call it auto edge constraint now. I keep saying line. So by default, it's turned on. Okay, so I can click on create edge constraints around the walls in this case and or floors, and I'll show you an example of both here. I can click apply. So by default, you can notice that they're all on. But I want to create a scenario where the edge constraint is turned off for this model, so you can see how the deflection changes if the edge constraint has been turned off. So I'm just going to go back to that same dialog box here, auto edge constraint, and I'm going to click on do not create edge constraints for that third model. Okay, so let's quickly run the analysis and see how the deflection changes. And we can take a look at some load distribution. Did I mess that up? Yeah. 1 second here. I accidentally took the edge constraint off here. Sorry about that. All right, I'm just going to turn it off for just the selected walls. Oh, I'm sorry, I forgot. Here it is, apply to full structure. That's what I messed up here. Okay, so now, there we go. Quickly run the analysis. Okay, so I'm looking at the deformed shape. So you can see here, the edge constraint is working quite nicely in this second wall, creating connectivity. Obviously not the case for the fourth wall. Connectivity only remains at the edge. No connectivity has been shown here in the middle, as you can see very obviously. Here, this third wall is kind of a situation where I created some area objects that manually manipulated the connectivity between the nodes, which worked out fine. It takes a little bit extra time. That's why manual meshing, it does take a little more time than, of course, the automated internal meshing. Okay, so graphically we can see how the auto edge constraint works. What about load distribution? How's the load getting from the top of the wall to the bottom? So if we click on display forces and stresses, we can take a look at the lateral X case, which had those 2 kips loads in the X direction. The F22 component, we'll click apply. So you can see there's a very uniform load distribution, of course, on the left-hand side of the wall, where all the nodes matched correctly. And take a look at this. So this is the edge constraint. The nodes were mismatched, but you have a pretty uniform load distribution from the top of the wall to the bottom, which is good to see. Same thing for the third wall. Fourth, not so good. See, you're only getting load distribution at the two edges of the wall, causing a very disruptive distribution from the top of the wall to the bottom. Okay, just another illustration of the auto edge constraint. So that was a very simple planar model for shear walls. But what if we have a floor slab? So here is a typical situation. We have a meshed floor slab here connecting to a wall as a part of an elevator core. So due to the edge constraints, you do not need to mesh this elevator core wall at these locations. Loads will be distributed automatically from the floor to the elevator core via the auto edge constraint tool. So in years past, of course, you'd have to go click on this wall itself, mesh the wall so that there are nodes located at these nodes on the floor as well to create load distribution. Not the case anymore. Well, this has been a part of ETABS for a few years now, so it's nothing new. Okay. Just other uses of the meshing tools available in ETABS. I'll keep on that same model here. And I think some of you are familiar with the draw openings tool here in ETABS. So what I did here on the top portion, just as I did in the previous model, I meshed the wall into 3 by 3. And you could select elements and delete them to generate an opening. That's one way to do it. Or there's something called the draw wall openings tool, which gives me the ability to drop in an opening in any location. I'm just going to arbitrarily generate one here. So I dropped in an opening and the specific wall. But the question is, okay, you put an opening in the wall, what about meshing? The answer is yes, I need to mesh this wall as well. You can't just put an opening in the wall and not have it meshed for proper load distribution. Okay, so what can we do here? So there's a tool that's been added. Again, it's been in ETABS for quite a while. So I can select the wall and the opening itself. And then there's a tool under Edit, Edit Shells, Divide Walls for Opening. Okay, so this is going to divide, it recognizes the location of the wall, the edges of the opening, and slice up the wall accordingly. So now, as shown in the wall here on the right-hand side, you can go and apply pier labels, spandrel labels, all those sorts of things. But proper load distribution will now be is now done correctly here for this specific shear wall. Okay, I know I've thrown a lot at you here, covering many different tools. Another common question is, okay, so sometimes I get errors when I mesh my model, and there's when I run the analysis, it says there's a meshing issue or there's an instability. So how can I fix that? Or what's a common tool that I can use? So I'm going to go to just this more simple model because it'll take less time. So I'm sure, again, most of you are familiar with the Analyze Check Model tool. Now, this is a very useful feature. It checks for tolerances, joint checks for connectivity for not only joints, frames, and shells, but what people don't know all the time are the check meshing for all stories. So this will essentially take a look at the mesh for every single story to see if there's issues. What is it looking for? It's looking for a disconnectivity. It's looking for overlapping meshes, overlapping slabs that are creating problems in the mesh. Slabs that are kind of hanging. They're not connecting to the joints all the way at the end. So it looks for these things, and it'll create we'll create a report. Again, this is a very simple model here. It's not going to probably not find anything. It says model has been checked, no warning messages were generated. But if there was a warning, they'd be listed all right here, as well as the area object in question. And then you can go ahead, take a look at the area object in question, maybe make changes to it. Usually the issues are connectivity. The area object is not connected to the column, to the beam, to a joint. Okay. Let's take a look at a couple questions here. I have some ones that were sent to me prior. Okay, one second here. Okay, just trying to get a couple of these. Excuse me. Okay, sorry about that. To correct, what are advantages of line constraints over mesh generators? Well, mesh generators can distort elements, so it can reduce solution accuracy, which requires more refined mesh to achieve certain levels of accuracy. So those line constraints I was talking about, they prevent element distortion, which minimizes the amount of meshing and enables efficient and accurate formulation. So you can use both. I use line constraints for proper load distribution, but I tend to lean towards the general auto meshing tool available in ETABS. So another question, when I'm meshing shells, how do I prevent the meshing failed error message? I just touched upon that, clicking on the analyze check model tool and take a look at the errors. It will tell you the exact location of where the initial errors occur. All right, so this question is there any way to edit the actual internal mesh nodes? Not physically. So of course, if you go back, if I'll just select an area object here, I go to assign shell, floor auto mesh options. Only thing you can change are, in this case, maybe the size of the maximum element size of the mesh. You can of course break it into certain pieces, but there's no way to edit manually the internal mesh nodes. And I understand that errors with these sometimes aren't easily resolved. It requires perhaps making a much more coarse mesh, because sometimes if the mesh is too dense, it gets really tight, especially in those corners where you have angles less than 90 degrees. I recommend making this maximum element size larger, so you're not getting those tiny, tiny triangular mesh element shapes that sometimes cause instabilities. Okay, a few more questions here. Does this function for mesh work similarly in SAP 2000? Yes, that is the case. Meshing capabilities are included in our SAP 2000 program as well. This is what happens to the frame loading when a frame is not meshed to the slab. By default, this frame is going to be meshed unless you tell it otherwise. So any frame loading will be automatically distributed to the shell itself. So just to show you an example, if I click on this frame, if I right click on it, you can see auto mesh. It says yes, joint internal. We can see what that means here. If I select the frame and go to assign frame, see frame auto mesh option. So by default, it's going to be turned on. The only way loads are not going to distribute from a frame to a slab is if I click on no auto meshing. And in that case, typically the loads are going to be distributed at the ends. Can you draw openings in a sloped wall? You can. You'd have to create, it's a little more complicated. You can create a view that's going to be planar with the floor itself, named view. What is it? Or let's see, what is it called? Developed elevation. So if you, well, that's going to be for elevations for sloped walls or curved walls. You'd have to create a named view in the same plane as the ramp itself, and then punch holes in it using the draw opening tool. A couple more examples here, or excuse me, questions. Now again, I just wanted to note that every question will be answered in a nice PDF format, which I'll post on the website, just because I wanted to include very thorough answers to some of your questions, which are a little more detailed. And that will be posted here today. So it looks like there's a few more questions that I want to save and will promise to answer in a nice PDF format. If you look on our website under the support tab, there's under support it says webinars. You can see all the pre-recorded or previously recorded webinars, as well as answers to all the questions there. So I think I'm going to end it now. Please look at our website at the location for answers to all unanswered questions here today. Thank you very much for joining me today. We're going to have some more webinars posted on our website. Please take a look at that in the very near future, and I appreciate all of you attending. Thank you very much.